In this next video, I'm going to talk about the assumptions that linear regression models make and some diagnostic tools for identifying violations of those assumptions, as well as other potential problems with regression models that don't directly have to do with the assumptions, but you still should be aware of. Here, I'm showing Anscombe's quartet again. You should recognize this from last week's lesson, and it illustrates some ways that regression models don't provide evidence for linearity. But drawing a line through some points doesn't require any assumptions on its own. The goal of drawing a line using OLS is to minimize the sum of squared residuals, and the line that we get as a result does minimize the sum of squared residuals. But of course, sometimes that line might be a pretty poor approximation of what's going on. Saying, I drew a line is not the same as saying that the points form a line, and reporting regression results is not the same as claiming that the points form a line. Instead, when you report regression results, what you are actually saying is that if you were to characterize the relationship between those variables as a straight line, this is the direction that line would be pointing. But when we conduct a hypothesis test of the slope of that line, see whether it's significantly greater than 0, then we are making some assumptions about how such slopes would arise due to chance, how they would show up randomly in a world where the data came from a process where the variables were independent. If we want to be able to make claims about how often a random data generating process would give rise to extreme slopes due to chance alone, in other words, p-values, then we need to be able to understand and characterize that random data generating process. And we usually do so by assuming a decent, hypothetical, general purpose random data generating process, specifically that the residuals are independent. They all come from the same distribution, and that distribution is close to normal. In other words, to use the p-value from the t-test of the regression slope, you want to feel reasonably safe in assuming that the observations are independent. There's no clustering or nesting. For example, if you did an experiment in a school to see if nap time helps student attention, and you randomized each classroom to have nap time or no nap time, and then observed the attention levels of the individual students, those students are not fully independent. Students in the same classroom were randomized together, and they of course might distract each other. That would violate the assumption that the observations are independent. You should think about this assumption mainly in terms of the structure of your experiment, not the statistical properties of the data. We design studies with things like independence of observations and randomization in mind in the first place. The main assumptions I'm talking about today have to do with the distribution of the residuals. The tests in linear regression assume that the residuals are close to normally distributed and that they all come from the same approximately normal distribution. That is, their distribution is similar throughout the full range of the predictors. We can break down this last assumption into two main parts. First, that the residuals have nearly constant mean. That is, the residuals are not much more likely to be positive or negative for certain values of the predictors. This assumption will be met as long as the underlying relationships are close to linear. And second, that the residuals have nearly constant variance. That is, they're not more spread out for certain values of the predictors. If the variance is higher or lower in some regions of the predictors, that's called heteroscedasticity. Another term for heteroscedasticity is heterogeneity of variance. Problems with the distribution of residuals can typically be found by looking at plots of those residuals. The key thing to remember is that none of these have strict cutoffs. Linear regression is a pretty reliable tool, and it chugs along just fine with minor violations of these assumptions. We just need to be aware of when we're violating the assumptions, how extreme those violations are, and what it means for the reliability of our results. The two main plots of residuals that are most conventional to look at are a normal QQ plot of the residuals. We use this to identify departures from normality, and a plot of the residuals against the fitted values. And we use this to look for heteroscedasticity and nonlinearity. Here's an example of a normal QQ plot of the residuals of a regression model. QQ stands for quantile, and it can be used to compare observed values to any distribution, not just a normal distribution. But when we use it on ordinary least squares regression residuals, then we're comparing them to a normal distribution. The observed quantiles in such a plot are on the y-axis, and the quantiles that would be expected from a perfectly normal distribution are on the x-axis. If the residuals are close to normal, then the QQ plot will be close to a straight line. The points will always go from the lower left to the upper right in a plot like this. The points in the lower left represent your negative residuals, the points that fell below the regression line, and the points in the upper right are your positive residuals, those that fell above the regression line. If your negative residuals are more extreme than would be expected from a normal distribution, then the points will veer below the line drawn on the QQ plot on the lower left. If your negative residuals are less extreme than would be expected from a normal distribution, then the points will veer above the line drawn on the QQ plot on the lower left. If your positive residuals are more extreme than would be expected from a normal distribution, the points will veer above the line on the upper right. And if your positive residuals are less extreme than would be expected from a normal distribution, the points will veer below the line on the upper right. Remember, we mostly use this kind of plot to identify departures from normality. In this case, the points are quite close to a straight line, shown on the screen, so there's nothing to worry about here. There are other normality tests that you can carry out on your residuals, but looking at a QQ plot is usually good enough. Remember, the point here is not to identify precise cutoffs, but rather to be aware of potentially concerning violations of assumptions, and these violations of assumptions are always a matter of degree. So this QQ plot is not particularly concerning. I'm going to show a series of other QQ plots that are also not particularly concerning. These residual quantiles follow a straight line mostly. The most extreme positive residuals appear to be less extreme than we would expect from a truly normal distribution, but the departure from normality is not big enough to raise concern. These residuals pretty much follow a straight line. Again, there will always be some departures near the ends. This one has some squiggles, but there's nothing concerning here. This one has small deviations, but again, small deviations like this are not a big deal. Here is a residual QQ plot that is more concerning. The residuals appear to be too extreme on both the positive and negative ends. That is, this distribution of residuals would have heavy tails compared to a normal distribution. This pattern would be hard to see with just a histogram, and so it illustrates why we use a QQ plot instead. Because a distribution like this would still look like a bell curve, but both of the narrow ends, the tails of the bell curve, would be just a little too thick, and it's hard to see that in a histogram. It's much easier to see it with a QQ plot like this. Here's a residual QQ plot with a very serious skewness problem. The residuals are right skewed, that is, the positive ones are too extreme, and the negative ones basically level off. A normal distribution should never level off anywhere. This is what a histogram of residuals would look like to create this QQ plot. And here's a QQ plot showing a serious problem with left skew, or negative skew. The negative residuals are too extreme, and the positive ones level off. And the histogram of residuals would look like this. Now the second main type of plot that we use to diagnose problems with residuals, a plot of the residuals against the fitted values, meaning the residuals are on the y-axis, the fitted values are on the x-axis. We use this to look for nonlinearity and heteroscedasticity. Nonlinearity should be fairly obvious. It would be apparent when these residuals zigzag up and down across the range of fitted values. Heteroscedasticity is, for example, when the residuals are close to zero on one end and get more spread out on the other end. And just like normality, there are other tests for nonlinearity and heteroscedasticity, but looking at a plot like this is usually good enough, because the point is not to identify precise cutoffs. The point is to be aware of potentially concerning violations of assumptions, and those violations are always a matter of degree. If you're concerned about heteroscedasticity, and it's hard to see in this kind of plot, you might also consider looking at something called a scale location plot. A scale location plot is the same as this, except that the residuals have been transformed by taking their absolute value and then taking the square root of those absolute values. That makes sure that they're all positive and the extreme ones get switched down towards zero, which makes it easy to see when they spread out in one direction. Anyway, this residual fitted value plot is not particularly concerning. I'm going to show a series of other residual fitted value plots that are also not particularly concerning. There's no zigzag, there's no funnel, the points don't systematically go up and down or get more or less spread out. Here, perfectly reasonable residual fitted value plot. Another perfectly reasonable residual fitted value plot. Again, no zigzag, no funnel, no concern. Now here's one with a problem. Specifically, there's a clear sign of heteroscedasticity here. The variance in the residuals is small on the left and large on the right. Here is one with a clear nonlinearity problem. If the actual relationship between your variables is U-shaped, then the residuals from drawing a straight line through those variables will be U-shaped too, because the straight line cannot follow the U shape, so it will kind of have to be horizontal, and then the residuals will just trace the pattern of the U. So if we see residuals like this, we should think about changing our model to account for this nonlinear pattern. Here's a different kind of nonlinearity problem. Okay, so the two main plots of residuals that we talked about were a QQ plot and a plot of residuals against fitted values. These helped us test some of the key assumptions for the t-test of the regression slope. The QQ plot helped us look for violations of the assumption that the residuals are normally distributed, and the residual fitted value plot helped us test whether there were systematic variations in the distribution of residuals along the range of fitted values, heteroscedasticity, and departures from linearity. You should notice something important about these assumptions. There is no assumption that the response variable or the predictors are normally distributed. I'm going to say this again because there is a common misconception about this. Linear regression does not assume that the predictors or the response variable are normally distributed. There is an assumption about normality, but that assumption has to do with the residuals, not the variables themselves. Think about all the examples that we've already done with binary predictors. A binary variable is about as far from normality as you can get, and yet there's no problem with including binary predictors in a linear regression model. You do need to know about the distributions of your variables anyway, even though the model doesn't make explicit assumptions about them. When you model continuous numeric variables with linear regression, weird distributions in your predictors and your response can contribute to all sorts of actual problems, especially if you're not aware of what's going on. But in and of themselves, the weird distributions of the predictors and the response don't explicitly violate the assumptions of the model. For example, you need to be aware of cases where your variables have outliers or skewness or an unusual number of extreme values. These problems can sometimes mess with the distribution of residuals, but just as importantly, they can create situations where a small number of observations have too much influence over your results. So you should get in the habit of knowing about the distributions of your variables for informational purposes before doing any kind of statistical analysis anyway, so that you know what to be on the lookout for. In a lot of psychological research, we want to avoid situations where a small number of observations have too much influence over the results. This isn't necessarily about model assumptions. Linear regression does not really assume that individual points can't be too influential. This is more about model interpretation. We would like to be able to characterize the associations between the variables that we've observed in a relatively general way. We don't want those associations to be due to one or two unusual participants in our sample. Cook's distance is a statistic that estimates how much influence each observation in the regression model has over the model results. Observations with extreme predictor values and large residuals will have high Cook's distance because they sort of pull the regression line toward them. We might look at the highest Cook's distances in our sample to see if we have reason to be concerned about those particular observations. For example, in this scatter plot, if I'm using x to predict y in the linear regression model, the point with the arrow drawn to it will have high Cook's distance because it will force the regression slope to come down a bit to avoid having its squared residual be too high. This is true even though this point is not an outlier for x alone. It is a high x value, but there's plenty of other high x values. And it's not an outlier for y alone. It's a low y value, but there's plenty of other y values. And this point would have looked completely ordinary in a histogram of x or y individually. I will show you the function for Cook's distance in R in a minute. Cook's distance greater than 0.5 would be very concerning. Even Cook's distances between 0.1 and 0.5 could be more influential than you want. You should check to see whether these points are outliers that you could mitigate with a transformation. Some sources recommend looking at any data points with Cook's distance above 4 divided by n, where n is your sample size. That metric is probably overkill, but you can always take a look at the highest Cook's distance values in any data set. You will always have a Cook's distance for every point, and so you can just look at the highest ones and decide for yourself whether those points seem to be doing something unusual for your regression model. The key, though, is don't just remove multivariate outliers like this. Instead, learn about how they affect the result. If you are concerned about how they affect the result, think about ways to report your results so that the reader really understands what's going on with the full data. Consider trying the analysis in a few different ways. Consider applying a transformation that reduces the influence of extreme points. After all, if you end up just removing all the points that don't resemble your hypothesis, then you're presenting an obviously biased view of the data.